Welcome back to linear algebra. In this video, I want to run through some properties of determinants, work through a couple of proofs, and get a little bit of a better feel of how determinants work and why they do some of the things that we are interested in. So let me get my head out of the way and let's jump right in. The first one I think is fairly obvious based on some of the calculations that we have done previously. Let A be a square matrix. If A has a zero row or a zero column, then the determinant of A is equal to 0. I'm not sure that I even have to write out the proof on this one, but I'll at least talk through it. We know that we can write out, or we can calculate a determinant by method of cofactor expansion. If there is a zero row or a zero column, we can expand along that column and we'll get 0 times each of several cofactors, giving us that a bunch of zeros are 0. Right? I'll try to write that out, but I'm not entirely sure that writing it out makes any more sense. Right? So calculate the determinant of A by expanding along the 0 row or the 0 column. And when you do that, each term in the cofactor expansion is multiplied by 0, the 0 that is that row. And so when you calculate the determinant, you get 0 plus 0 all the way down through to just a bunch of zeros, and add them together, you get 0. I love this kind of proof, and if you go further in mathematics, building up a confidence to write proofs like this becomes more and more valuable, where we make arguments without having to write much of anything in the way of calculation. This is what mathematics really looks like when mathematicians are actively working. Um, the second result also should be very obvious based on how we calculate the determinant of a matrix. Let's let A, and it's going to be useful to us to have the components of A. Aij is the ith row, jth column. And all told, we have an n by n triangular matrix. And from that, I can claim that the determinant of A is the product A11, A22, all the way down to ANN, all of the entries on the main diagonal. And the key here comes from the fact that this is a triangular matrix. So I know that on one side or the other of this diagonal, we have all zeros. I set this up as a lower triangular, and in a lower triangular matrix, we're going to want to expand. That's not visible. We're going to want to expand down columns. So we get A11, and then we expand down the first column again, and we get A11 times A22 times, and eventually we just get A11, A22, all the way down to ANN. Because every other entry is going to end up with all those zeros involved and just goes away. Right. If we had a lower triangular matrix, then instead of expanding out columns, we would expand out rows, and it would work the exact same way. You saw evidence of this in the calculations that we did in the previous video. I'm just codifying it. Although it does allow me a corollary that the determinant of the identity matrix is 1. And of course, the identity matrix is a diagonal matrix, and every diagonal matrix is a triangular matrix. And so we can use that theorem I just went through to say that the determinant of I is the product of all of the entries on the main diagonal, and every entry on the main diagonal of I is 1. So there we have it. Right. As a corollary, I often don't write out the proof of a corollary. It doesn't take that much work, but it is something that is interesting. Moving along, let A be any square matrix. Sorry, not just any square matrix. I actually do need the dimensions of it. Let A be an n by n square matrix. And for any n by n square matrix, the determinant of k times that matrix, I claim, is k to the n times the determinant of A. For the sake of expediency, for the sake of trying to make this a reasonable length, I'm not going to prove this for every matrix. Excuse me. I'm not going to prove this for every matrix. I'm going to assume that A is triangular. Right? So again, I'm not proving the theorem in general, but I think that this will give you an idea of where that comes from, and it should make a lot of sense. As we saw in our previous theorem, the determinant of A must be the product of the diagonal entries A11, A22 down through to ANN. Well, K times A has entries that are K times Aij. So the determinant of Ka. All right, first of all, If A is triangular and we multiply each entry in A by K, then any zero entry is still zero. And I can say that Ka is also triangular, and I can calculate the determinant the same way. The first row, first column is going to be K times A11. The second row, second column is going to be K times A22, all the way down to K times ANN at the end. If I bring out all of the Ks, there are N of them. And it leaves behind A11, A22, all the way down to ANN, which is exactly the determinant of A. All right, once again, my assumption here that A is triangular means that I proved something other than the theorem I wrote. Although I hope that it gives you some good insight as to why this is going to be the result. I don't think I'm going to ask it because actually writing out the proof in general is just incredibly tedious, and I'm not sure that it gains you that much. But you should have the ability to write out the more generalized proof using the basic idea we have here and the more broad idea of cofactor expansion. You can set up this same thing and you can start to get the feeling that this is going to work in general. I probably won't ask you to do it in general, but I might ask you to do it for a 2x2 or a 3x3 case, which is mostly manageable. It's a little bit unpleasantly long in writing, but not conceptually difficult. Another one, kind of the same vein. Let A be any square matrix, then the transpose is also a square matrix, and I claim that the determinant of the transpose is equal to the determinant of A. Right. Once again, this is going to be something that I ask you to prove on your own, but just a quick reminder that if A is Aij, then A transpose is Aji. We swap the rows and the columns when we take the transpose. All right. The proof of this one is fairly straightforward. I will ask you to try to set that up on your own. For now, I want to go to kind of the big one. Of the operations we have on matrices, scalar multiplication, the transpose are fairly straightforward. Powers and inverses are incredibly complex. There's a lot going on there, and it all builds on multiplication. We also have the tool of matrix addition. Luckily for building up, matrix multiplication is incredibly well behaved around the determinant. Unfortunately, matrix addition is not. To see what I mean, let's take a look at a particular example. Right? Proving these theorems in general is a little bit tedious, but I think seeing an example helps to get the point across. Let's consider a couple of 2 by 2 matrices. Matrix A is the matrix with components 2, 1, 2, 3. And matrix B is a 2 by 2 matrix with components 5, 1, 2, 1. We can find the determinant of A. Determinant of a 2 by 2 matrix is fairly straightforward. 2 times 3 is 6. 2 times 1 is 2. 6 minus 2 is 4. The determinant on matrix B, 5 times 1 is 5. 2 times 1 is 2. 5 minus 2 is 3. If I add these matrices together, A plus B, 2, 1, 2, 3, plus 5, 1, 2, 1, is going to come out as 7, 2, 4, 4. And if I take the determinant of A plus B, that's going to be, well, 7 times 4 is 28. 4 times 2 is 8. 28 minus 8 is 20. I don't see an obvious way to get from 4 and 3 to 20. There is no relationship between determinant of A, determinant of B, and determinant of A plus B. I guess I should say there's no simple relationship. If I try matrix multiplication, on the other hand, let me copy the top half of this screen so that I don't lose that information. You don't need to rewrite it. You can see up half a page in your notes to where that was. But let's go ahead and take a look at A times B, right? The result of multiplication of 2, 1, 2, 3 times 5, 1, 2, 1. Right? Row dot with column. 2 times 5 is 10. 1 times 2 is 2. 10 plus 2 is 12. 2 times 1, 1 times 1, 2 plus 1 is 3. And we get 10 and 6 is 16. We get 2 and 3 is 5. And now if I take the determinant of A times B, I get, well, 12 times 5 is 60. 16 times 3 is 48. And 60 minus 48 is 12. Right away, I hope you notice that the determinant of A times B is equal to the determinant of A times the determinant of B. Right? Actually proving this is unpleasant. I could record an hour or so video just walking through that proof. I don't think that you would gain much from it. There's not a lot interesting that comes out of it. But here is a nice illustration that it does actually work. Not the same as a proof, but sometimes helpful. But that theorem that we just established, that the determinant of a product of two matrices is the product of the determinants, allows us to prove a good portion of this theorem. Let A be any square matrix. If the determinant of A is non-zero, then A inverse exists, and the determinant of A inverse is 1 over the determinant of A. If the determinant of A is equal to 0, then A inverse does not exist. Right? I'm not quite going to be able to prove all of this claim, but I'm going to be able to prove a good portion of it. If A inverse exists, then the determinant of A times A inverse is equal to the determinant of A times the determinant of A inverse, right? That's the theorem that we just established. The determinant of a product is the product of the determinants. But by the definition of the inverse matrix, A times A inverse must be the identity matrix. And so, substituting that in, I get that the determinant of A times the determinant of A inverse is equal to the determinant of the identity matrix. And we established near the beginning of this video that the determinant of the identity matrix is 1. And from here, the arguments are fairly straightforward. If the determinant of A is not equal to 0, I can just divide both sides of this equation by the determinant of A and get that the determinant of A inverse is 1 over the determinant of A. That part is fairly straightforward. What happens if the determinant of A is 0? Well, then the determinant of A inverse is some number which you multiply times 0 to get 1. Right? If the determinant of A is equal to 0, then the determinant of A inverse is equal to 1, and 0 times anything is that thing, so we get that 0 equals 1. All right. I didn't quite get as far as actually proving this theorem. It's the second time I've said that in this video, but I've proven a lot of it. If the determinant of, or if the inverse exists, then the determinant of A must be non-zero, and the determinant of the inverse is 1 over the determinant of A. Because if the inverse exists and the determinant of A is 0, I get that 0 equals 1, which is nonsense. All right, so it must be the case that whenever the inverse of a matrix exists, the determinant of that matrix is not 0. That's not quite as far as saying that every time the determinant is non-zero, the inverse exists, but it is a long way towards it. It turns out that that last step is true. Proving that last step of the proof, again, a lot of work, not a lot of gain. Let's focus on This part, which I hope will help you understand that relationship, and also the fact that whenever the inverse exists, the determinant must be non-zero. All right. So I want to wrap this video up asking you to spend a little bit more time thinking about the fact that the determinant of a product is the product of the determinants. Choose any two 3x3 matrices. I'll give you the hint that if you choose triangular matrices, you're going to find this to be quite a bit easier. But you can choose any matrix you would like. I'd like you to multiply those matrices together, find the determinant of each of your original matrices, find the determinant of the product, and show that they match up and they follow the theorem. Again, it's not a proof of the theorem, but it's some evidence to help you remember that it does, in fact, always work for any matrices. All right. That's all I have on this video, so take a few minutes, see what you can do with that, and I'll see you next time.